What is the data? Well, we are supposed to be at the time step tn plus 1, and I know some data from previous time step. Typically, the ones that I know is the strains at the previous time step, and the internal variable r evaluated at the end of the previous time step, which is the beginning of the current time step. And then I know also as the data, because the model is driven by the strains, I know the current strains. The strains for which I want to compute the stresses. Okay? This I know at the beginning. So these are data, input data into my routine. First step, let's compute the effective stresses, which are the elastic stresses, the stresses that would be returned by an elastic algorithm, so using the standard, elastic model that you are using, C times epsilon. And, of course, in terms of that, I can compute the norm of the strains, which can be expressed as the effective stresses times the strains, and also at time n plus 1, and just in case I don't have it here, just the norm at time at the end. Okay? And then I'm able to compute the taus, the norm of the strains, at the point n plus alpha that I'm using for my alpha integration method. So depending on what is alpha, I just multiply that times 1 minus alpha and that times alpha, and I obtain that. That's first step. Preliminary data. Step 2, integration. Here I have to distinguish two cases. Elastic unloading, neutral loading case, which is just checked, and we saw that we can check, in principle, we should check that in terms of how is the tau, the norm of the strains, at the time n plus alpha, the point n plus alpha, with respect to r n plus alpha, which we don't know, because this would depend on r n plus 1, which is, that would be a nonlinear loop, something that we see. But we have shown that we don't need to do that. Just by checking with respect to r n, I know, I can determine which is the current state. You realize the advantage? So now I check that. If that is smaller than this, I'm sure, smaller or equal, that I'm in elastic unloading. What happens in elastic unloading? There is no evolution of r. So Rn plus 1 remains frozen, the same that I had. No evolution of d, because this depends on that. And the stresses are just driven by the evolution of the effective stresses of this part. Okay? And what is the algorithmic visco damage tangent constitutive operator? 1 minus d times a. Exit. Get out. Then, if this is not the case, so the other case, this tau epsilon n plus alpha, included here, is greater than Rn, again, I'm comparing with Rn, not with Rn plus 1. Then, I know that I'm in a loading case. And then, Rn plus 1 is driven by the algorithm we have plotted derived before, that in terms of eta, alpha, whatever, and Rn, which I have, tau epsilon n plus alpha, which I have computed in step 1. Once I know R, I know D by replacing in Q, and then I have that new damage variable. Then new stresses are the effective stresses multiplied by 1 minus D. That I have now stresses. And then, what is the tangent constitutive operator? Algorithmic tangent constitutive operator, the one that we have in the formula, which is the second one plus the second part here. This is something that can be checked in terms of, you see, you can recognize here a lot of the properties that we have mentioned before, the alpha, the alpha integration method, delta T, viscosity, hardening modulus, everything is evaluated at the corresponding time step. I mean, conceptually, it's trivial, and this product here. Okay? And then, in that case, just I take these stresses, this C and this R, and exit the routine and go to the other part of the program where I'm going to use the stresses and the tangent constitutive algorithmic tangent operator. And that's it. I don't know, you don't know to do anything else. You don't know to do now another routine for the implicit case. In that routine, that's just entering here with eta equals 0, then you have the implicit case. Okay, eta equals 0 and alpha equals 1. You have the implicit case. So only that, which should be maybe 20 lines, it has taken 10 hours for me to explain this, but finally we arrived. That's optimal. That's like a picture for a painter. That's something that you are satisfied saying, I've just condensed it. That is what computational mechanics is. Devising algorithms, which are robust, efficient, accurate, and whatever, and have control. And that we can just code in a finite element code where everything is under control. This is the way to doing it. Look at the algorithm, check that everything, and then once you have the algorithm, just implement it. Okay? That's a good case. And then you should be able to do experiments. For instance, imagine that's something that you'll do in the assignment. We'll take the assignment will be at this stage just in one point, so we don't look at the structure. We look at one point where we enter some strains and we enter some stresses. And then, for instance, we will, depending on the properties, we have for a strain, for instance, for the implicit case, where the rate of strain is very small. So the strains change a long time, but very small. Then, or even for eta equals 0. Anyway, for no strains, the result would be 1, and then you should be able to check what happened when you increase the speed at which you apply the strains. So in the same interval, you apply more strains, or the same strains are applied in a shorter interval, then you should expect different results. Which ones? That's up to you. That's something that you have to report on in the segment. Also, effects, you should be able to check the effects of viscosity. If we enter now eta equals 0, then you obtain some response. If you now increase the viscosity, you should obtain different results. Even for the case eta equal 10 to the 5, 10 to the 13, you should be able to get some result. Which is that? Something that you should report. Okay? And depending on what you report, we will realize if you have done the job well or not. Okay? That's that. Well, just a little additional consideration. In fact, most of us are engineers, and we engineers like, I always say this in my classes, we like simplicity. We like everything to do as simple as possible, to do the minimum work. That's inherent to engineers, okay? That's something, there are many examples for that. And this is an example. Look, everything that is in here is written in normal tensor notation. So you see that here I have strains, C is a fourth order tensor, this is double contraction, this is double contraction, etc. This is a second order tensor. Of course, this can be coded. Of course, this can be done, and then doing the loops corresponding and do the operations and so on. But that could be simplified essentially due to one thing. Strains and stresses are second order symmetric tensor. And then, if we look at the structure of this tensor, for instance, a strains, let's consider the Cartesian system of coordinates. This is the strain tensor, an infinitesimal strain tensor so far. So these are the typical elongations, and these are the tangential strains, etc., etc. But look, this tensor is symmetric. So this term is equal to that equal to that equal to that. And sometimes engineers just write this out of diagonal terms in terms of the angular strains, which are twice this. Okay, so this is the way. So these are elongations, and these are gamma xy, gamma xz, gamma yz, the angular strains, and this part is symmetric to that one. So here is where engineers came, one engineer at this point, and said, why do I have to work with 9 numbers if only 6 of them are similar, are the same, sorry. Because these can be known and justified as we know that. And said, why do I cannot introduce another notation in which instead of talking of the tensor of strains, I talk about a vector of strains. A vector of strains where these components can be placed here in a certain order. First, the 3 elongations, the 3 diagonal terms, and then, in terms of the strains, the 3 shear angles. Look that we do not introduce the 1/2 here, and that there is for something. That's the reason for that. Okay? Of course, that if I know that, then I would be able to reproduce that, placing that here, that here, that here, that here, divided by 2, etc., etc. So that's not the problem. About the stresses, the stress is the same. It's the Cauchy stresses, the true stresses, or whatever you want to call them, then is a second-order symmetric tensor. By the way, there are other stresses which are not symmetric. Maybe you know them, but other stresses that are used in other contexts, Piola, Kirchhoff stresses, and so on, are not necessarily symmetric. But the Cauchy stresses, which are those, are symmetric. So again, I just can build a vector on R6, which has 6 components in 3D, which just reproduce first in that order the elements of the diagonal, and then the elements out of the diagonal in that order, that, and that. Okay? Look that the order is the same. And here there is no 1/2 to be discussed. Well, there is a very important property. If I do the double contraction product of this times this, which in fact is multiplying every term by the corresponding one and summing them up, okay? That's 9 summations. And I do the vector, the dot product of these 2 vectors. These are vectors in a space of 6 dimensions. So the product of this vector is this component times this, plus this times this, plus this times this. This is what we call the single contraction. So the single contraction of these 2 vectors, vector of a strain, which is denoted by these brackets I put here to emphasize it, and distinguish that from that. This is a tensor, this is a tensor in R3, that's a vector in R6. So the dot product of this vector times that gives the same result of the double dot product of this tensor times this one. And you get just it. And by the way, in this game, it's very important the 1/2 here, because this product is repeated here and there, and 1/2 of 1/2 gives 1, which is the one which is replicated by this. Anyway, check it yourself. So what does it mean? That, in fact, the only complex operations I have to do would be multiply double dot products that appear in several places. Here, no? You see, for instance, where? Here, no? Here, these operations, and operation can be replaced. Instead, every time that it appears epsilon times a vector here, I can replace them by the vector of effective stresses, 6 components, times single dot product, the vector of strains. Okay? So it's much simpler to code, much effective. There is no repetition of computations and so on. Well, what happens with that? Well, it can be also proven that this equation here, that relates the tensor of stresses is equal to a 4th order tensor, isotropic tensor, times the double dot product times the strains, where this is a structure here, so this gives rise to some expression, can be replaced in the Voigt's notation, saying that that vector 6 times 1, 6, vector 6, column vector 6, is equal to a matrix. That matrix is what is called the elastic constants matrix, which can be computed that way in terms of the Young modulus and the Poisson ratio. Look that this matrix is also symmetric. It's a 6 times 6, because this is a vector, 6 times 1, this is a matrix, 6 times 6, and this is a vector, 6 times 1. Okay, so it's consistent, the matrix product. So by doing matrix product now, this matrix times this vector equal this vector, that is equivalent to that. And the vector of the stresses that I will obtain will be the same that if I had used this operation here. And that's much easier to code, because then that is just a matrix product. Okay? So again here, whenever I see that in the algorithm, whenever I see C times epsilon, I just put D, the 6 times 6 matrix, times the vector of strains. And then this is a vector multiplied by then a new vector stands here. So typical expressions like that emerge. Well, we'll see. Anyway, also the inverse. You know that it's possible to invert the Hooke's law, and that is the so-called C minus minus 1 is lacking here, minus 1, which is given in terms of mu and epsilon, and we can replace this equation by a vector equation in terms of the Voigt notation. The strains in Voigt notation, vector, is equal to one matrix which is 6 times 6, which is called the compliance matrix, elastic compliance matrix, which is the inverse of G, by the way. If you take that matrix and you take the inverse, you will obtain that matrix. And can be computed in that way, in terms of E and mu. That's it. And G, you can here recognize the, do you recognize this one? Is that what? The shear modulus. Oh, okay.
Is this the matrix characterized for a specific type of problem, like plane stress?
No, the general 3D. Of course, it's isotropic elastic. So there are only two parameters, mu and E. You have to characterize, or whatever you can. Two parameters only. Okay. So now, the algorithm. I'm not replacing all the algorithms. So just telling you what operation. For instance, computing the norm of the strains. This is a scalar. We can do that, but in fact, you can do just the product, the dot product of the vector of effective stresses times the strains. Okay? Or epsilon d epsilon, these being vectors, and this is the matrix. Or sigma d minus 1 sigma bar. It's exactly the same that we did every time that in the initial formulation we have double dot. What is right and left, we just put the vectors, and whenever we have C, we put D. C minus 1, D minus 1, etc. Just that's so. It's trivial. It's trivial doing that. And this is much easier and much faster because you save a lot of operations, by the way. And well, this for instance, the tangent constitutive operators. Of course, if we talk about an output here, which is the tangent constitutive operator, which is 1 minus d times C, what do you think it will come here? Instead of C, it will come D. Okay? And this will be, instead of a fourth order tensor, that would be a second order tensor, a matrix 6 times 6. And what about here? This is a scalar, it's not going to change. This is a scalar, all this is not going to change. And this is the open product of two tensors. The open product of two second order tensors is a fourth order tensor, which is consistent with the fact that this is order tensor. But now, what is coming to your mind for replacing here? The open product of the two Voigt vectors of the stresses. Okay? Which is what you have here. Open product. How do you compute that? This is a 6 times 1 is a matrix. 6 times 1 is transposing that, multiplying that times that. Okay, that's the open product. The transposed of the first multiplied by the transposed of the second. First is 6 times 1, and this is transposed 1 times 6, so that is 6 times 6, which is a matrix consistent with that. Well, it is. So easy. Of course, in your assignments, you are not going to work in 3D. We're going to work in 2D. So everything holds anyway. Instead of having epsilon as a second order tensor in 3 times 3, it's 2 times 2. Again, the Voigt notation says the strains are epsilon x, epsilon y, and then the angle of the formation, the shear of formation, gamma xy. Okay, in that order. Every time you have that, also for the stresses, sigma x, sigma y, tau xy. In fact, you should be able, if you were interested, I don't recommend you can change the order of those and nothing happens. Wherever it is consistent, you can change the order of some of them, and you can change the order of some of them. I recommend you to use the standard, which is this. Okay? And don't forget here is 1/2 here. Huh? And then it's the same. So instead of that, we have some D. Instead of C, we have some D, which is 3 times 3 now, because we have the strains are just 3 components. Okay, 3 times 3. And here there is a difference, which is specific for plane stress or plane strain. In fact, again, in this intention of doing the things as simple as possible, we can always use the same expression for both. But then, here, we use the real values of E and U, and here, for plane strain, we use the corrected values of E and U. According to the spread, in terms of the real ones, the bar means the corrected values, which is the way that you have to correct the ones for plane stress to obtain the ones for plane stress. So you code just that expression, and the input for that expression is just the original E and nu or the corrected E bar or nu bar. And that's it. Okay? And that's it.